Section 3.5, Exponential and Logarithmic Models. The equations we're going to look at today model growth, decay, or follow a very common logistic growth curve that will be given to you in this sort of form. So the first scenario that we're going to look at is either growth or decay. Now, what we have to do here is kind of take this information that's given to us and create the model. So these are the pieces that we use, but sometimes given the situation, we have to figure out them before we can answer the question. So in our first example, we have a population of fruit flies that's increasing exponentially. So that tells us it's going to look like one of these two models. Obviously, if our b is positive, it's growth. If our b is negative, that's going to be decay, because obviously with the negative exponent, that's going to make numbers less than 1 that we're multiplying by. Now, we're given information. For instance, after 2 days, there are 10 flies, and after 4 days, there are 300 flies. So at the end, we need to figure out how many flies will there be after 2 days. Well, the thing is, these two pieces of information are given to us to help us create the model first, because we can't answer any questions about it until we have a model to actually work with. So to begin, we want to go ahead and solve for the a and the b. Okay, so depending on the situation, we may know a just because that can sometimes be looked at as an initial value, which makes sense because oftentimes x is time. So if we let 0 go in there, that makes this whole term here just 1. So when x is 0 initially, a is our initial value. So sometimes we get that. Now in this case, we have information after 2 days and after 4 days. So we don't right off the bat know what our initial amount is, so we don't actually know a. So what we need to do is kind of model this like a system. So what we want to do is think about what does these two pieces of information in there look like to find these two missing variables, the a and the b. Because to work with this model, we need the y and the x to be the only variables. So first off, let's identify our model. So in this case, the model we're looking for, of course, is going to be that y equals ae raised to the bt. Or I should say bx. I like to put t for time, but we'll just make it x to match. And for step 1, we got to solve a system. Okay, so let's just make a note here. Solve system. Because we have two pieces of information. When we plug those into the equations, we can have two of those. Okay, so solve system, and we're going to solve it for b. Now, because of the way the equations look, this is not going to be an elimination scenario where I'm actually going to plug this in and use substitution. So let's go ahead and take our first piece of information. After 2 days, there were 100 flies. So I can put the 2 in for the x, and I can put the 100 in for the y, because the y is the amount of flies, the x is how many days have gone by. We got to figure out, for this particular model, what the a and the b is. So if we jot that down, we can say that 100 flies happen after 2 days. So then we have our a, e, and then, of course, raised to the b times 2. Okay, so there's our first piece of information. Now, the second piece of information was that there were 300 flies after 4 days. So we have our a, e to the b times 4. So as you can see, we have two equations, right? Both of them, because we've plugged in for x and y, with unknown a's and b's. So we have a classic system. So the easiest way to go about this is to solve for b. So that's kind of what we want to get here. So we want to figure out what is b. And once we figure out what b is, it's really easy to find a. So let's go to our first equation, because I want to use substitution, and let's figure out what does a equal, so then we can plug into the second equation and get the value for b. So if I go to my first equation and get a by itself, that means I got to take my 100 and divide it by e to the 2b. Because that's what we're multiplying a by. Okay, so again, we just took this piece here, divided it over. Now, because we want to do substitution, we're going to take this expression right here for a and substitute it in right here. So in our second equation, we have 300, but instead of writing a, we're going to write the 100 divided by e to the 2b. And of course, that's still being multiplied times e to the 4b. So now all we have to do is solve this equation for whatever b is. So first off, let's clean this up. On the left side, we have 300. Now on the right side, we have 100. And when you want to simplify these e's, this is in the numerator because we're multiplying it on the outside. And clearly this one's in the denominator. So when you're dividing like bases, you subtract their exponents. So the 4b here minus 2b is going to leave me with e raised to the 2b. Now, to figure out what b is, we have just a regular exponential equation. So what we're going to do is divide by 100 and then rewrite. So if I divide by 100, we have 3 is equal to e to the 2b. So rewriting tells me that the natural log, because this is a log base e, of 3 is equal to 2b. So that means if I go ahead and get b by itself, the exact answer is going to, when I divide by 2, be 1/2 times the natural log of 3. Now, if you can leave it that way, or if you want to make it a nice decimal, this is going to be approximately 0.5493. And I really suggest going at least 4 places. And the reason for that is when you're getting these numbers right here, you want to go out a decent number because especially with exponentials, any smaller difference between maybe 549 and 5493 when you're multiplying, exponentially can really show up. So either leave it like this, or if you prefer just putting a number up there, go at least 4 decimal places. Okay, so again, now that we've solved it for b, which as I've demonstrated, I think is a little easier than going after a directly, now for step 2, now we solve for a. Because once you find b, you can just take that and plug it back in and get a. And remember, the smart move is to take our answer, right, the thing we got, and plug it, right back into where, we had that. So we're going to take our number and plug it right back into this equation here, because a is equal, in terms of b there. So that means to find a, I'm just going to take 100 and then divide it by e raised to the 2b. So that's going to be 2 times that 0.5493. There we go. Okay, and if we punch that up and get a decimal, it's about 33.334. Okay, so we have our model, right? So given our 2 pieces of information, 2 days, 100 flies, 4 days, 300 flies, I'm able to write an equation for each. Taking one of the equations and solving it very easily for A, I can substitute that in, solve the exponential for B, right? Get that decimal, plug it back in over here, and get my A. Now the good news is, now that I'm here in my step 3, now I can just write the model. Because I figured out for this particular scenario, given the information they gave me, what the A and the B is, okay? So remember, our goal is to come up with something that looks like this once we figure out A and B. And then when you write the model, you should have the variables of X and Y, where X is however many days have passed and Y would be the population of fruit flies. So if we go ahead and put all these pieces together, the model is going to be Y equals our A value, so 33.334, times E raised to the B value, which was that 0.5493 times our X. So this model right here is something we can use, right, to finally answer our question, because we have our X here, that's the number of days, and our Y is the number of flies. Our question wants to know how many flies after 5 days. So to do that, again, all we got to do is plug in a 5 for X. So we'll take our 33.334 and raise that to the E times 0.5493. And again, we're going to plug in 5 days here. Now typing in our calculator and simplifying, this gives us approximately 519.610 flies. And clearly you could, interpret that to be about 519 flies, but just to be precise, that would be to 3 decimal places. Now let's look at an example of logistic growth. Here we're given the model, and the situation is that there is a discontinuing of advertising for this toolkit beginning in 2007. Now the manufacturer noted that the sales began to drop, and this is the model that shows that drop. We want to estimate the sales in 2015, and then we want to figure out in what year will the manufacturer end up selling 200,000 units, or kits, in this case, toolkits. So when we look at this model here, if we are going to first estimate the sales in 2015, that means we're going to plug in for T and solve for S. So that's just basically a calculator problem. The second part of it is to figure out in what year will we actually know we're selling 200,000 kits. That means we know we have the 200,000 here because, of course, S is kits, and we're going to be solving for T. Okay. Now remember, T equals 7 is the year 2007, so essentially T is the number of years after the year 2000. S, again, is the number of kits. So basically the first part here is plug in for T, figure out S. The second part is plug in for S, solve for T. So let's estimate the sales in 2015 first. So to do that, again, we're simply going to solve for S using our calculators. Okay, so we're going to take our 500,000 and then divide that by 1 plus 0.4 raised to the 0.004, not 0464. And then because we're looking for, in this case, the year 2015, that means what we're going to do is plug a 15 in there because T stands for, again, the number of years past 2000. Since we know, T equals 7 corresponds to the year, 2007. So if we plug that in our calculator, that's going to give us about, 462865.0, if I round 3 places, 011. So that's about 462,000 toolkits that are sold that year, okay? Now, again, that's an easy one because if we simply want to estimate the sales, in a certain year, you just plug in for T and punch it up. There's really not a lot of solving to happen. So that's actually a very straightforward, easy one. Now, the other side of it, of course, is let's estimate, given a certain number of kits, when that will happen. So maybe we're curious, how long is it going to be until we end up only selling 200,000 kits, right? Obviously, in 2015, we're still, up about 462,000. But when will it be down to 200,000? So that means we're going to put that number here in for S and solve for T. So we put our 200,000 in for S, and then we have our 500,000 in our numerator here, plus 1.0.4 E 0.0, I keep doing 0, 0 on that. 0.046, and again, here's the big difference. We're solving for T. Okay, now, just like our previous problems when we're solving here for an exponential, our job is going to be to get this by itself, rewrite it as a logarithm, and then punch it up. Now, the problem in this one, unlike our last models, is it's in the denominator. So we've got to figure out a way to get that out of the denominator. So I think step one is going to take this whole denominator here and multiply it over here to the other side. Therefore, no more fraction. Now, when I do that, obviously there's still 200,000 over here. So essentially, when I multiply this entire denominator up here to the left side, we're going to multiply 200,000 times the 1 and 200,000 times the 0.4 e to all this. Okay, so I'm going to distribute the 2,000 to both these pieces as I multiply it up there. So when I distribute the 2,000 each one of those, we get 200,000 times 1. And then when you would take the 200,000 times the rest of this, really you just multiply times the 0.4, and that's actually 8,000. And you're still, of course, multiplying that times e to the 0.046 4t. Just realized I forgot a 4 up here. We'll fix that. And then this equals our 500,000. So now that I've gotten this out of the denominator, I can easily remake this and do the rewrite by subtracting 200,000 and then dividing by 8,000. That will get the e stuff by itself. So if I subtract 200,000 and divide by 8,000, that's going to leave me with 37.5, and that, of course, is equal to the e to the 0.464t. Okay, so that got it by itself. Now we're going to do our rewrite. So it's the natural log of base e, log base e, or natural logarithm of 37.5 is equal to 0.0464t. And our last step, of course, dividing the natural log of 37.5 by 0.0464 tells me that t is going to be approximately 78.111 years, right, after 2000. So if you wanted to just give a general year when that would happen, t is basically in the year, not t, but it's basically in the year 2078. And that's sometime during that year, just a little past probably January, February, where you're going to be hitting 200,000 units sold.